received the ERC starting grant, which is great. Congratulations. And yeah, she will be talking about understanding and mitigating memorization in Foundation.
Thank you so much for the kind introduction. So welcome everyone. And indeed, today I'm going to talk about the first pillar of my ERC grant, which is concerned with privacy and large models. And the work that I'm presenting today is not work that I've done alone, but it's work that we've done mainly with our group, the SprintML-Lab with Cisco, that is colleague with Adam. And our lab does not only work on the topics of privacy, but we also work on other aspects of security and robustness and interpretability, like under this broader umbrella of trustful. And yeah, we are currently a group of roughly 20 people from 6 different nations. And yeah, if you want to find out more about our work, you can always visit our website. And the work that I'm presenting today is in some form of a broader scheme of things. So basically, we have a long line of work on memorization where we looked into different types of models, and we tried to, in the first place, define what memorization even means. So what does it mean for machine learning models to memorize? And we did that for vision encoders, and we did that also to not only understand how we can quantify memorization, but also how we can localize it inside the models. And we also investigated as a first work a formal definition for memorization in text to image, like clip style encoders. But today I'm more going to focus on the generative model part, which I think is these days the state of the art. And there we have applied our work to first localize where memorization really happens in the models, to then design based on it achieve mitigation for memorization that I'm going to talk about. We have analyzed memorization beyond this binary level of being memorized versus not being memorized. And this parsed it basically into a memorization of the foreground and of the background, which helps us to really understand if some, for example, sensitive objects are memorized. And finally, we're currently working on understanding more of dynamics, like how memorization emerges. So with that, let's get started. So we have nowadays these large-scale models, like diffusion models, that generate photorealistic images. And therefore, they are trained on large amounts of data. But what is a problem with that is that these models are able to retain, that means to memorize their training data, and then at inference time, output near exact copies. And if this is like a private image, like a face or like private health record, of course, this yields privacy risks. And before we started working on the topic, there was, of course, work that has tried to mitigate the risks. And we can broadly group the types of defenses that have been proposed in 2 families. There's first the training-based family, which then identifies after the model is fully trained, what are the memorized samples, and then kind of retrains or fine-tunes either without them or either tries to unlearn those. The problem with this kind of approach is that they're usually expensive and damage might already be done if you have already shared a model. The second type of mitigations that we identified is the inference-based mitigation. So there was plenty of work that looked into how does it even emerge at inference time. So we take a model and then, for example, we infer, we give it a prompt, and then we analyze how does the model behave on the prompt. And based on this behavior of the prompt, we can identify which samples might be more memorized than others. And then at inference time, have some safeguards. For example, if we see that there's too much of an alignment between the text prompt and the generated image, then we would at inference basically block it. But this comes with a lot of delay, and that comes with extra models that you can add, and it's really not suited if you want to deploy the model locally, like an open weight model. And therefore, we designed a new mitigation that kind of approaches the problem differently, and we call it MIMO. And what MIMO does is it's finding neurons that are responsible for memorization. So it goes into these large diffusion models and identifies which neurons are main responsible for memorized samples, which then gives us a possibility to identify the single neurons that are responsible and basically swap them out and basically thereby mitigate memorization. And to understand how this method works, I'll just go briefly again through the generation and training process of diffusion models, because this will inspire how the method is eventually run. And on a big picture, diffusion models generate images from noise. So you give it noise, And then potentially for text generative models, you give it also a text prompt. And then based on that, it will generate you a picture. How this is done basically is by, in training, presenting your training images, noise with different levels of added noise. And then you have the model predict what was the noise that has been added to the clean sample, such that then afterwards you can have a loss between basically what you really added in terms of noise and what the model believes you added in terms of noise. And you can backprobe over this loss. So this eventually teaches the model to do the correct denoising step. And then if you at inference time now give it some noise and the caption, and you say you want to see the image of a cat in the forest, then basically the model predicts the noise. And all you have to do is take your original image with the added noise, or like your original noise, and you subtract the predicted noise. And over time, basically, you have already like a slightly less noisy version. And you do that over time. So you have multiple generation steps. And thereby you then have eventually generated an image. Now, what prior work has found is actually that this distribution of the noise paths, so how we denoise something, can give us quite a good intuition on what samples are memorized. And what they found is that the noise trajectories on memorized samples are significantly more similar to each other than on non-memorized samples. So imagine now you have a non-memorized image. You give the model a different random noise. This means just a different random vector. And from there, the model will start denoising. And because the model has no information, has nothing seen about it, from every random seed, it will kind of denoise differently. So it's like a very random process. But what happens if you have memorized samples is that the model pretty quickly collapses to the same denoising trajectory. Because during the training, it has always seen this noise with a prompt, and it knows which image it should actually converge to. So eventually, the noise trajectory for the memorized samples will be significantly more similar. And this can already be seen, as was shown by Van et al., in the first denoising step. Just to show you how this basically looks in practice, if you take these memorized prompts here, like this hippopotamus, and then you denoise it, and here basically every column is a different random seed, so a totally different random noise that we start off from. But you see always already after the noise trajectory converges immediately into this hippo shape. And this is not how diffusion models normally work. If they don't memorize a sample, then you give it 4 different noises, and all the noise trajectories will look pretty much different. So what is this is of course something which is very interesting, where you put an inference time, and when I'll have an inference time used it to then prevent the model gradually from generating. But it's pretty expensive, and you have to do it for every generation anew, and always detect and then generate and then potentially roll back. So that's not super practical. But we can use that as a practical guidance for our memorization mitigation. So first of all, we need a score how to quantify whether we are collapsing to the same denoising trajectory. And therefore, we use the structural similarity index measure. This is the SM score. And this can basically be used to always analyze where does the noise converge to for different random seeds. So we start different random seeds. We do the first denoising step. We see how similar are these noises. And this can give us an idea of how whether we are currently working with a memorized sample, and also whether memorization has actually been mitigated. So if we now look into just the data set that we worked with the COCO data set here, and we found that basically if you look into non-memorized samples, then you are here with this SM score, overall different noises don't collapse into the same noise trajectory. That's what we empirically saw, just once again quantified here. And then there are 2 types of memorization that prior work had considered until then, which is the verbatim memorization. That means it regenerates the data 1-to-1, and template memorization, which means it was never fully defined, and we're going to get to that later in the presentation. But it just means it takes some elements from an image. And what you see is that here the structural similarities are significantly more different. So if that was, for example, your sample, then a template memorization could kind of look like this, where it copies this carpet, but it doesn't copy really the rest of the room around it. And the verbatim memorization would copy basically the whole thing. So now what we do is that we use this information and we take the diffusion model to find neurons that are responsible for individually memorized samples. And how we do that is with a simple kind of outlier finding strategy. So we take a batch of images and we take a batch of memorized images and we infer both through the model. And we store the activation at every single neuron. And then we look at every neuron, how outlier the activation of the memorized sample is. In a formula that would roughly look like this, where we have the z-score basically here of the neuron I at layer L, and we have the text prompt that guides our generation. Then basically the score here is the activation on this particular prompt, for example, our memorized prompt, versus the mean and standard deviation of activations of this neuron on other data points. And basically what we then see is that the memorized samples that are kind of local in some neuron, they have a very high z-score because their activation on the neuron is very different than from other data points. So this neuron basically specializes in those. And if we now look into what are the z-scores actually, so then we see that non-memorized samples, like on all neurons, kind of have a 0 z-score, which means their activations are common. So like they activate neurons just like any other data point. But if you look into memorized data points and how they activate neurons over the whole network, you'll see that their score is pretty much dispersed. So you have outliers in both directions. They either activate it very high or very little. And if you now have these kind of scores, what we could already do as a naive thing is to say, whenever a neuron has such a high score that is basically higher than some threshold that we define, then we could say this neuron is memorizing that data. Are there any questions so far? Otherwise, I'll go into how we made that better, because what you can see here is that this still is kind of a large part of the distribution. So there would be multiple neurons, like many of them, which have this kind of anomalous z-score for the individual data points. This would mean that if we want to target neurons, and we would, for example, want to switch them off, we would have to switch off a lot of them. And this then eventually would harm the performance of the model. So
So to like, for example, define it as if the portion of the CDF, for example, to the right of the threshold is big enough to just turn off the neuron. Is that or?
So like you could say set an arbitrary threshold. This would be kind of our naive baseline. You set an arbitrary threshold and say every neuron that has a higher activation on this given image than the threshold would be switched off. So like that's something you can definitely do, and that's something that we show works. The problem is just it degrades the model performance because we switch off many neurons, and this kind of like harms then the model. So what I'm going to present next is how we improved over this naive baseline to like localize more individual neurons. And this is basically done with a with a two-step approach, where we first do a kind of coarse grain candidate selection, and we just by looking at the data through a validation set, we find that like an initial activation threshold of 5 is kind of okay. And then additionally, we also keep the neurons that have the highest activation overall. And we say that, first of all, everything that fulfills this criteria is considered memorized. And then we look into the candidate neurons and we switch them off. And now here comes this SIM score, which is going to be very handy, because like if you don't have this SIM between the initial noises, you would have to generate a full image to understand whether it's still memorized or not. But if you can, from the first denoising step, already see with a structural similarity whether or not the image is still memorized, this of course saves you a lot of time, because instead of running like hundreds of denoising steps, you run one, and you know like has the memorization status changed. So if the structural similarity between the noises is still super high, it means it's still memorized. If the structural similarity is lower, then you see it's not memorized anymore. And so like this, you decrease like one by one the threshold until you like it's kind of, you can also use a binary search. We tried out different strategies to narrow down basically from which like threshold on you are able to deactivate the memorization. And then once you have your candidate set, then we do some form of refinement. Because now, like eventually after this first step, we usually still have roughly 100 neurons that are possible candidates to memorizing the data point. And in the refinement then, to be computationally expensive, we go layer by layer and then neuron by neuron. So like first we switch off all the identified neurons in a given layer. If it changes something on the memorization, then we know, okay, now we need to look into individual neurons. If it doesn't change anything, we can move on to the next layer and basically discard all of those from the candidate set. So eventually in this refinement step, we end up with a very small subset of neurons that we then know are responsible for the memorization. And so just to show you now, like some initial results here, when we look into doing this technique and then switching off the neurons that we identified with our NEMO technique versus random neurons, and we look into the metrics. So we do have two metrics. The SSCD score is what we measure then eventually in the final images to understand whether the image is memorized. And the SSCD is also like a similarity score. And if it's high, it means that the images are still very like similar. So what we want, of course, after memorization removal is that the image before removal and after removal are not similar anymore. So let's see what happens if we deactivate random neurons. Well, unfortunately, the image that we generate or the images that we generate with the memorized prompts are still on average extremely similar to the original ones. And you can imagine like this model we experimented with Stable Diffusion 1.4 and 1.5 has millions of parameters. So like switching off 4 random neurons shouldn't be really changing the behavior. And it's kind of like a baseline to see that just randomly switching off neurons doesn't help. But then if you deactivate the 4 neurons that NEMO found, what you see is that eventually like the score here is significantly lower. So the similarity between the images that are generated for the memorized prompts before and after our intervention, they are now very dissimilar. So that means basically NEMO successfully manages to remove the memorization. And of course, there's a second objective that we want to keep, which is that if we afterwards measure the performance, and we do so just using the clip score between the text prompt and the image, then we want to still have a high score, which then shows us that our image quality is still good. And we see that there is nearly no degeneration. So after all, like NEMO is pretty good in doing this like removal of memorization without harming model performance. And just now to give you some like also qualitative insights. So this is a memorized example with different seeds. Before, it always generated the same image. After our NEMO intervention, where we switched off only 3 neurons, it still generates the same person, but not the memorized image anymore. So our goal is achieved. And basically this you can run over all the memorized prompts that we know, and you see that often, like even there's as little as 1 neuron responsible for making the generation of this entire image. So just to quantify that, we also measured how many neurons it takes to really unlearn or like dememorize the memorized images. And what you can see here is that for the verbatim memorization, often as little as a handful of neurons are sufficient to prevent the model from outputting the memorized samples. For the template memorization, it's a bit more, but still considering that there are millions of neurons in this whole network, this is really comparatively little. There are also some interesting findings that we made about like memorization clusters, which is that some neurons seem to be extremely prone to memorizing, and we are trying to understand what they actually memorize. So there was this famous neuron 25, which when switched off, directly affected like 15 different memorized prompts, and we're kind of trying to make sense of it. And what we eventually could find as a similarity is that they are all the memorized prompts that were memorized in this neuron 25 were kind of related to celebrities. So eventually, like the neuron 25 would be the celebrity neuron, and switching it off basically like prevents memorization of those samples. And just as a final quantitative insight on the performance that we keep with NEMO. So to unlearn all the 500 memorized prompts that we have, it takes roughly 750 neurons. This is because like some prompts are memorized by the same neuron, some neurons contribute to multiple prompts. So to unlearn the whole set of memorized prompts that we know, it takes these 750 neurons to be switched off. And we then looked into the FID and KID score to just understand like how does performance evolve, and like the lowest score is better. And what you can see is that our approach stays roughly around the baseline, definitely in the standard deviation. So at least in this setup here, we have not harmed the model performance significantly. Now, what you can expect, like it's going up here a bit, the more you want to unmemorize samples, also like expectedly, the more the performance goes up. But given that multiple neurons, like the same neuron is responsible for multiple prompts, we expect no explosion basically on how much the performance will degrade over time. And taking it from there, it's pretty cool. What we then set out to ask in the follow-up work that we are currently working on is the question, does that mean that memorization is local? So does it mean that like indeed like there's this one single neuron, and once this is gone, you will never be able to get those memorized samples out again? Because this would be extremely cool, because then you could just release the model, open source, the open weight, and you would never have to bother about privacy concerns anymore. So what we did is like to ask the question, is it only one of these neurons that is responsible for generating the prompt? So what we did for that was to actually go a bit beyond the initial experiments in the NEMO work. So our follow-up paper, Finding Dory, is actually looking into the text embedding space. So like so far I've been abstracting a bit from it. What happens actually when you give this noise and the text? The text, of course, is not presented to the model as tokens or as text, but there's some form of embedder in between, which makes a text embedding. And given this text embedding in noise, then the model can generate the images. So what we then experimented with is, can we optimize this embedding to still give us this image? So we started off with the original text embedding here, for example, the name of the person and the brain blocks. And we took that embedding, and this embedding itself did not generate that image anymore. So this is why NEMO was successful. But now what we did is to do really some optimization to say, okay, optimize this text embedding by backpropping over the model to get eventually this image out again. And it turns out we can. So the text embedding can be optimized to again map to this image. And we also even went further and we analyzed what happens if we don't initialize it with the original text embedding, but with any text embedding in the embedding space, just like a random vector. Can we also optimize a random vector to generate this image here? And the problem is, yes, we can as well. So this means for us that the memorization is not local. Like it means as well that you can, like if nobody with malicious intents gets your model, if people can only input text prompts, then you're likely not to trigger the memorized samples. However, if somebody comes with malicious intent and has access to the open weights of the model, then by optimizing the text embedding, they can achieve like to bring back the memorized samples. What was a possibility that we considered is that we could just force the model to generate any kind of image. Therefore, we did an ablation where we studied what happens actually if for non-memorized images, we try to force the model to just generate that exact image by also optimizing a text embedding. And so we went from the original text prompt and from other text prompt and did 50 optimization steps for both non-memorized and memorized samples. And what you can see is that for non-memorized images, even though we get something visually pretty similar, we do not in our setup manage to recreate the image. Whereas for the memorized samples, we eventually get the same image back. So this means like our method doesn't just show that we can force the model to generate anything, but indeed shows that the memorized data is still deeply ingrained in the model and our optimized text embedding just brings it back. To look into that a bit more quantitatively, also, if we have basically our non-memorized prompts, and we look into the memorization metrics here, like these are the same metrics basically as before. So the higher the SSCD score, the more memorized something. We also have the memorization rate, which is like which fraction of the memorized images we can bring back. And we have like the FID score. And what we see for the non-memorized prompts, we eventually still do not basically pretend that they are memorized, or we don't like make them behave like memorized samples. So even if we do this story-based optimization, but for the previously memorized samples, what happens is that if we just do these optimizations over the text embedding with Dory, the model can still generate them. So this is an indicator that memorization is not local, and that mitigations indeed in the future should, like, if you want to release the model open source and open weight, that you need to update the entire model to have a more holistic learning. And in the paper, we present an initial approach on how to do so. In another follow-up work on this one that I just want to briefly mention, we do something more, and I've already hinted at it. The prior work, including our own, had only looked into these two categories: verbatim memorization, where data points are like output directly the way they were seen in training, and template memorization, where template memorization was this rough thing saying, well, like maybe they are just kind of similar, or they have similar elements. And to get more understanding of this, of this kind of non-verbatim memorization, we developed a new metric that classifies memorization into foreground and background memorization, where you can then basically like quantify the templates better. So you can then identify, like, are the main objects the same, or is it just the same structure? And for example, the same structure is often not so, at least in real world cases that we saw, was often not so problematic, because eventually it was, for example, these sample t-shirts. You have a t-shirt shop and they always have the same sample, but then it's like swap the t-shirts and then like it's just like the background is memorized. But you could imagine that there are setups where this kind of background memorization is exactly the problem, where you, for example, have an MRI scanner, and the MRI scanner always takes the same picture of the same lung in the same position. So but then basically the body structure will be different for everyone. So in that setup, the memorization here might be indeed like crucial. And so this metric will hopefully in the future guide the community towards like better understanding of memorization beyond that binary metric. And like just to give you a few examples, like we already saw the verbatim memorized like VM samples in the previous presentation. Verbatim memorized means like the original image looks exactly like the generated one. And then new samples that we could identify as foreground memorized. So here the foreground is like this backpack, and like this is in the training image, it's a black background, but in the generated image, it's the gray background, but it still looks kind of the same. And for the background memorization, it's these kind of sample images which I've been mentioning. So like the main objects, like this pillow here, for example, between original sample and generated sample, they look different. And the backgrounds, they look the same. So now with that metric, basically, we will get a better understanding on how much individual parts are memorized. And just to bring everything together, I brought our final results on that here. So what we found, like for different like neuron numbers that are switched off with NEMO, with like if you just measure the verbatim memorization, then you will find that it's a very small number. So you will expect that NEMO is already kind of successful. But if you now use our new metric and you also quantify this background and foreground memorization, you see that you will have much larger numbers of data points that are still being memorized, either their foreground or their background, which shows basically that the other metrics, they have been underestimating the privacy risk, which again highlights the need for new methods to really unlearn with more like rigor. And with that, I'd like to thank you. And I'm very happy if there are any questions.
Yep. Do we have any questions of Franziska? Yes.
I have a question. So how do you know that it's not possible to manipulate the prompts instead of the embedding to go back to the memorized image?
So what we found is that like, we did try some searches, but the prompt space is a discrete space. So you cannot do very like meaningful searches there. What we did eventually, like for like the hundreds and thousands of embeddings that we did optimize to get the memorized samples out, we tried to map them back into the text space just to see if that would be successful. But there's always some loss, right? Like the optimized embedding might like doesn't match 100% to a token. So you do have some distance there. And eventually it was never possible for us with the optimized embedding to go into the text space and then still trigger the memorized sample. So they seem to be, I'm thinking of it kind of like adversarial examples where the perturbations are minimal to really trigger this. And if you go into this discrete space where text is located, you will not be able to be so fine-grained.
Thank you. Do we have any more questions? If not, then let's thank Franziska again. Our next speaker is Adam Dziedzic.